shows up, often asking the question, how do I go from linear differential equations to sample difference equations? And how do I look at those connections and how are those things related? And so we're going to take a discussion about it. If I imagine I have a canonical second order low pass filter differential equation. So second order, first order, and notice a tau squared, tau over q, and so forth. And I need to sample this, and so I'm going to have some sort of sampling time. It's very typical expectation. I would start off by realizing my concepts for derivative and second derivative are basically difference of things. And in fact, I can imagine that what I'm going to be able to do is get really close to whatever my sample rate is, because that's going to be my smallest time scale, and that's what I'm going to effectively use for that point. And so it's like a y of n minus y of n minus 1. If I do this carefully, I can certainly start to show I can even get things that make sense in a frequency domain space. Second order, I can second order domain space, no problem. But then you start to say, well, what's the difference equation look like? And yes, there is also a whole theory in talking about solutions on a digital machine of how you do differential equations. And that gets you much more formal case. But a lot of times I want an approximation that I can run on my digital, simple digital system, and I want to be thinking about it from a signal processing perspective. So if I imagine that I have A, which is going to be tau over that sample time, this differential equation turns out into this difference equation. You can see where the second derivative is, the first derivative, and so on. And so the question is, well, how good is this? Well, I certainly get a nice z transform from this. One thing I know is that for at least where omega is small, that's usually when you think omega much smaller than 1, I might imagine that this term here looks very close to a j omega squared term. This would look like a j omega term. You can kind of see that from the basic approximation of 1 minus e to the minus j omega hat would just be like approximately j omega hat. That'll work for it being small, but small only gets you so far here. And we'll illustrate this in two different cases. But you can see for this structure, this would give me a nice frequency response, as well as obviously I can have my z response. Now, if omega is small, it's going to give me a nice, what I would expect for that classical second order time, sort of second order structure, which would fall as right out of the Laplace or Fourier transform of this PDE, or this differential equation. So that actually helps quite a bit. So you might go, well, cool. Well, how does it look for these cases? So let's look at two cases. One where A is 4 and Q is 4. So A being 4, meaning if my sampling time is 4 times the time constant. And A being 1 means my sampling is right at the time constant. And I pick Q equal to 4 and 1 just to kind of illustrate some interesting pieces here. And what you notice if I look at the frequency response and I plot it in log of sampled frequency, a log of sampled omega versus transfer function. So this is going to go up to pi, which is why it stops at 3-ish or so, because that's where it's going to stop. And goes, close to 0 and be relatively constant all the way back, is that in fact I do get a similar response. How similar? Well, certainly at the very lower frequencies, 0.1 and so forth, it's not bad, but then eventually it starts to break off a bit. Still not bad here, and I can certainly see the boundary condition for the repetition right at pi. Similar thing when I go q equal to 1, but I push it out further, because if I push this in, it would look better. So I wanted you to see it. And if you push it out a bit, what you notice is that, yeah, I do see this is the continuous one. For a while it works until I get to 0.1, but strangely, even the sign breaks in different directions. Qualitatively similar, but not quite the same, but close enough to get a sense of, well, this is how close things are. And I think there's always this assumption of that, well, I can make everything look perfect. It's not perfect, but I can certainly work with it and it's manageable in this linear situation.